Welcome back to the show that tells you you are a quantum computer with free will, dematerializing and rematerializing into new space-time realities. My name is Justin Riddle, and this is episode 21 of the Quantum Consciousness series. In today's episode, we'll be talking about quantization in quantum mechanics. The idea that reality is fundamentally digitized, and this leads to some peculiar violations of our naive sense of how reality works. By the end of today's episode, we'll ask the question, is the perception of movement fundamentally an illusion? This episode is available on YouTube, and an audio-only version is available on Spotify and Apple Podcast. If you like what you hear today, then please like this video, subscribe to this channel, leave a comment below, or for the audio listener, write a review.
Join me deep inside the mystery of numbers. Come and huff a metaphysical glue. See how concepts become objects and then become qualia. Join us for an episode of Quantum Consciousness.
Hey there, I am Justin Riddle. So I got a PhD in psychology from UC Berkeley, and while I was there, I taught a course on quantum consciousness. And I taught this course for 7 years, and this podcast is really an update of that material, an extension of it, and then, giving it to a wider audience. In my day job, I am a cognitive neuroscientist, and I use electrical and magnetic brain stimulation in humans to better understand the role of macroscopic, slow-wave electromagnetic fields in the human brain and how they contribute to cognitive control, memory, and attention. All right, so the topic for today is quantization. So I'm going to start off by giving a little bit of background on how quantization might have been hinted at by early philosophers. Some of the evidence that came out of quantum mechanics to establish the quantization of energy and systems in our reality and physics. And then what that really means for our sense of self, for understanding the world as a quantum computer, as a digital computer, as the interaction between these different forms of computation, and then end by speculating on what this really means for our sense of self and how it relates to our experience of reality. So I'm going to start off by talking about Zeno of Elea, who is a Greek philosopher from roughly 450 BCE. And he had a series of paradoxes that he presented, and a few of these were really compelling and sort of predicted the realization that reality is quantized. And so I'm going to start off with the most common one, which is there is a race between Achilles, a Greek god or demigod. I'm not too familiar with Greek mythology. And he is known for his athletic prowess. And Achilles is going to race against a tortoise, an animal that is very slow in the animal kingdom. So to make this race somewhat fair, we're going to give the tortoise a head start, and the tortoise is running along this path, this track that the two are racing on. And of course, the tortoise is very slow, but let's say it gets 100 meters ahead of Achilles, and then Achilles begins the race. And so what we're going to do is we're going to basically look at the distance between Achilles and the tortoise, and we're going to look at it at distinct snapshots. So if we watch Achilles catching up to the tortoise, because he's much faster than the tortoise, we note that he is halfway caught up to the tortoise. There's about, let's say, 50 meters between the two. Now we jump a little bit further, and there's only 25 meters between the two. Note that they're both moving forward. And then we jump a little bit forward in time. We're 12 and a half meters between the two. And then we're roughly 6 meters. And then 3 meters, 1.5 meters, 0.75 meters, right? We're getting closer and closer and closer. And the distance between Achilles and the tortoise is shrinking. And it keeps shrinking and it keeps shrinking and it keeps shrinking. But what happens is that he gets infinitely close to catching up to the tortoise, but he never actually catches up. Why does this not make any sense is the question. Because we know, common sense, Achilles should be beating the tortoise, and yet here we have an infinite regression of getting infinitely closer to catching up, but never quite catching up. The same can be said for we have a distance between you and some point in the future. Let's say you're walking into the park. So you're at your house, you're walking to the park, and you get 50% of the way to the park, another 50%, another 50%, another 50%, and you get infinitely closer to reaching the park, but you never actually get to the park. So what is this? There's this precipice that you can never quite cross, where you're never actually stepping foot into the park. All right, the final paradox is the arrow paradox. So we have an archer who shoots an arrow, and we want to observe the moment that the arrow moves from here to there, right? So it's shooting through the air. We're going to pause the arrow mid-flight at location Y and pause it at mid-flight in location X. And we're going to try to find, where is the moment where it moves from X to Y? Because at time point X, we freeze it, and the arrow is just floating there in the air. It's suspended, it's frozen in time, and it's not moving. We go look at Y, this position in time and space slightly ahead in the future, and we look at the arrow, and it's not moving. Okay, and so it must be moving between these two, places. So let's go halfway between these two time points, and we look at it, and again, a frozen arrow, just suspended in the air, motionless. And so we're diving and diving and diving, and we're trying to find a moment where the arrow actually moves. So we're getting closer and closer to, let's say, time point X, looking at finer and finer grains of time, zooming in, trying to find a moment where the arrow actually moves from here to there. But what we find is that the arrow is always stationary. At any snapshot that we can view, it's always stationary, and it's, position here and position there. It's moving slightly further in space, but there's never a moment where it's actually moving. It's always just floating in the air. And so this is Zeno's paradox of time and paradox of space. And so what is wrong with this framing of space and time? Essentially, the assumption going into this is that space is continuous. There is an infinite number of regions of space between two locations, and there's an infinite number of moments in time between two moments in time. And I think this is a naive sort of intuition that a lot of people have. You just kind of assume that there are an infinite number of spaces between 2 points and an infinite number of moments of time between two moments in time. But if this is the case, then you could have things like Zeno is describing, where you have an infinite zooming in space as you're walking to the park and never quite getting there, infinite zooming in time, where you're trying to look for this moment of change between two time points and you never quite see that change. And if you assume that it's continuous, then these thought paradoxes or these thought realities that don't make any sense are possible. And so what Zeno concludes is that space is not continuous and time is not continuous. So therefore, space must be discrete and time must be discrete. And another sort of impossibility that this brings up is the idea that everything that we look at appears to be motionless and timeless, right? If you take any snapshot of reality, everything is frozen in space and time. And we've never actually really seen things move if you think carefully about this. And so I know what you're screaming out there. Yes, I see things move all the time. Well, we're going to try to break that sense of intuition that you have about motion, because things definitely are moving through space and are moving through time. But how do we better understand this? Because in this way of viewing everything as continuous, we run into these weird paradoxical realities. So the solution to the Zeno's paradox is that time is discrete, space is discrete. So as I'm moving to the park, there's actually only so many space chunks between me and the park. and you can quantify them. It might be very large, but as I move, I'm moving a countable number of, let's use like an example of like a checkerboard. I'm moving a certain number of checker spaces towards the park. And eventually I hit a point where I'm just one checker space away, and then I just move that checker space, and then I'm at the park, right? So there's a way to overcome the continuum, and we're defining everything as moving between you're in this location in space, then you're in this other location in space. And there's no such thing as like, if you have location A and location B, there's no halfway point between A and B. There just is location A and there is location B, and A.5 or negative B minus 0.5 doesn't exist. There is only A and B. And this kind of breaks our mind in how we typically think about the world around us as continuous. Similarly, with time, the arrow is moving through discrete moments in time. There is not an infinite number of time points. There's time point A, there's time point B, there's time point C, and the arrow is either in time A or time B or time C. You cannot zoom into time and find A.5, B.5, C.3792, right? There is only these discrete moments in time, and you move between them, and you cannot be in flux at the center point between one or the other. So this feels really weird. It doesn't really feel right on some basic level. And this is also reflected in the history of science. So our theories about space and time were based on this notion that reality is continuous. And so we were creating these models of reality and modeling everything as a continuum of space, continuum of time. And we're tracking the position of something in space and time, and we're modeling it continuously. But these models led to some weird predictions that weren't mapped onto the data. Or more so, the data was weird and the models were very perfect and simple. So the first example of this is the example of black body radiation. And there's plenty of materials out there, so I encourage you to go search for videos that dive into this particular concept. But just to give you some broad overview of what this was, as you view a body that is, or a physical object that's emitting electromagnetic radiation, you find that it's not a continuum of electromagnetic radiation. There's actually packets of electromagnetic radiation that are coming out of this other object. And so you might think, as temperature is varying, you see this continuum of what gets emitted, but actually at the extreme ends, there's either an emission or there's not. And it's sort of this binary, digitized packet of energy that gets emitted or it does not get emitted. And the same observation was also observed soon after that discovery in the context of light. So Max Planck discovered the quantization of electromagnetic energy, and then Einstein quickly used this to apply it to light, where light was originally modeled as a continuum, right? The sun is emitting these waves. It's a continuum of light, but there's observations where if you look at some material like an atom, it wants to absorb light, and it can only take certain packets of light, and then it jumps between different energy levels. And so you can look up more of this material on your own, but the takeaway message here is that light is fundamentally digitized, quantized into packets called photons. And so there's a photon, and it has a certain wavelength, a certain energy associated with it, but they come in individual particle-like chunks of light. And these observations are the birth of quantum mechanics. And so the word quantum refers to quanta, referring to the quantization of reality into discrete units. So you have a unit of light, a unit of electromagnetic radiation, and so everything has this digitization. And what this was later extended to realize is that space and time have the most fundamental unit associated with them. So we have Planck time and Planck scale, And these are the smallest chunks of time and space that are theoretically possible. And so space is like a checkerboard of different regions of space and different moments in time. And there is no space or time between these different Planck scale units, right? So we truly live in a checkerboard reality where everything is quantized. Systems are quantized. Everything around you comes in little chunks and packets. And also space itself and time itself at a fundamental level are thought to be quantized. And so going back to that arrow of time, the arrow getting shot through space, and we're trying to figure out these different moments of time. There is only this time and that time, and same with space. There is only here, there is only there. There is not a continuum of different spatial locations and different moments in time. All right, so what does this mean? Well, I think this really breaks our notion of reality, because as we look out in the world, we see things as moving continuously. And so what is motion? If there is only this location in space and this location in time, how do you go from one position in space and one moment in time to another position in space and another moment in time? And so the solution here is that while the universe is digitized, the wave function is continuous. So there's this probability distribution, this superposition of multiple different space-time realities, which are digitized, and this wave function is riding on top of that digital reality. So this is where those like three worlds that I always talk about come in. So if we just focus on the physical world and the mental world, we're drawing a clear distinction here. There's the physical domain, which is digitized fundamentally, and then there's the mental world, which of course is like, a leap, an association, but that mental world is a superposition, it's a wave function. It is able to represent a distribution of multiple digitized realities, right? So then what is movement? Movement is you get measured, you get collapsed, you get locked into a digital state, some space-time geometry. You're here now. And then you go into a superposition of multiple different locations across time, and then you get measured again. Some other thing comes in, collapses the wave function, you get locked into another location, and now you're there at that moment in time that you get measured. And so movement is the transition of being measured in this space-time reality, going into a wave function of neighboring locations, and then getting measured again in that new space-time location. And so the wave function is evolving. There's this evolution of the wave function through time, and that evolution is the movement, right? So the evolution takes place, you're localized here, and then it spreads out into the neighbors, and now you occupy this like distribution of being in all these different places at all these different times simultaneously, and then you get locked into another place. And so as we watch something move, it's evolving, getting localized, evolving, getting localized, evolving, getting localized. And what's really bizarre is, like, if you look at your body moving around, your body is actually getting digitized into a space-time reality, going into an evolution across multiple space-time realities, and then digitized again. And this is happening super fast. It's imperceptible to us, the scale at which these things are occurring. And so as you look around you, you're observing movement, but all of these movements are collapse and evolution, this sort of cyclic process happening under the hood, behind the scenes. We're often not aware of this occurring. So the question here is, how does all this chatter about quantization relate to the mind? And so I'm pitching to you that the body is digital. It is this digital computer, right? It needs to be measured. It's in this space-time reality. You're either a 1, you're either a 0, and the digital framing of reality lines up very closely with this notion of quantization, right? So you can get measured, you're in a 0 position or a 1 position, And we have these stable states that are physical, they're able to be maintained through time. And then you have the quantum computer, which is sort of an evolution of these quantum bits, which do not have to be locked into the 0 or the 1 state. And they're like an evolution or like an oscillation between the 0 and the 1 state. And you create this single quantum computer, which is all of these different quantum bits working together and evolving through time. And so as you're getting measured or getting digitized, you're locking into some space-time reality in this digital phase and then evolving, and you're able to move and you're able to change because you enter into this quantum evolution state. And so the mind seems to be more synonymous with that wave function, with that evolution, but behavior, perception, all this stuff that needs to pass through the digital computer is fundamentally getting digitized, right? And so Stuart Hameroff, Roger Penrose, when they talk about this quantum computational model of mind, they suggest that as the mind is evolving through time, it's having these discrete moments of now. So they draw the association that your experience has a bunch of these discrete moments in time as the mind is essentially digitized. And so your experience, according to them, is like a bunch of discrete moments, a flickering, a snapshot, and there's this flickering reality. And that flicker is the rate at which you're experiencing life, and you're getting new information in this, digital evolution, this movement of the mind through time, getting changed into different space-time configurations. But I think another way of viewing it is that if you're the quantum computer and your mind is somehow synonymous with that wave function itself, then yes, it's getting digitized, but you could still have a bit of continuity in your experience. So yeah, this quantization is not to say that there is nothing continuous in reality. In fact, the wave function and these probability distributions seem to add that continuity, that continuous evolution on top of this digital environment, right? So there's these two worlds interacting, and maybe your mind does have a continuity to it. It does have a sense of moving through time. And while time and space are digitized in some sense, there's also this quantum computational level, which might be genuinely flowing and not be digitized. So, the Penrose-Hameroff model tries to digitize your mind fully in some sense, where these discrete moments of time are occurring, and maybe that does set a pace to your experience. But it doesn't quite write out the fact that you could have a continuous experience of reality. All right, so let's revisit this notion of movement. So then, what is movement? Once we start introducing quantum computation as a fundamental aspect of reality, and check out the previous video on quantum computation, the idea is that everything is actually a quantum computer. And when you plug in a bunch of systems together and you have these like special conditions where quantum coherence is established across a bunch of different quantum bits or quantum systems, you make a more macroscopic quantum computer that does more interesting things. But fundamentally, every photon, every electron, all these like really basic particles or systems are also quantum computers. They're just not computing things that are that interesting, perhaps. So then what then is movement? And so the idea here is that movement is a quantum computation. All movements are the transition from this space-time reality to a new space-time reality. But how does it go from here to there? It evolves into a superposition, a probability space of all these different realities. And quantum computation is harnessing that evolution because it has inherent computational properties. It's essentially calculating some sort of energy distribution, minimizing energy expenditure. And so this computation is a naturally evolving process or a naturally occurring process. And so movement is a form of computation, and time or the evolution through time is fundamentally computational. And this is why I totally reject this notion of time as like the fourth dimension. It just seems like a really weak metaphor to just call time a spatial dimension when there's so much more to time. There's sort of this unitary evolution from the past into the future. And so I think here, time is this movement. Time is closer to this quantum computation. It has a forward trajectory as the computation is running. And while it gets digitized either by chaotic actors in the environment or through this internal self-collapse, which probably, is less entropic, check out previous episodes. Nonetheless, that evolution through time fundamentally is a computational process and seems to be closer to, one of these generative elements of our reality that gains in complexity, builds meaningful structures through time, and is sort of closer to our evolution and how we came to be in this reality as such a complex, higher order being, where fundamentally movement is shaping and sculpting reality towards greater order in some way. And so, I question you to think about your notion of time, think about your notion of movement, and how this is most likely fundamentally a computational process, and yet everything passes through the digitization phase. So your reality is digital. Everything around you becomes digitized. Everything comes in these packets. Quantum computers are composed of a bunch of different quantum bits, these quantized, countable numbers of quantum bits. And then that forms this macroscopic entity. And reality is fundamentally this interplay between this continuum level and this digital level. And we're somehow stuck in the middle and trying to break down our naive assumptions about how reality works. So I'll let you ponder that. And then in the next episode, we'll be talking about the quantum Zeno effect, which harnesses this sort of digitization, and it talks about the evolution through time. And it has a lot to do with maybe how our brain is able to interface with our quantum computer mind. So more on that next week, and I'll talk to you again real soon.